Hi, welcome back. Now let's understand the bonding in metals and carbonyl compounds, particularly carbon monoxide, so to say. The homoleptic carbonyl compounds containing carbonyl ligands particularly are formed by most of the transition metals. These carbonyls have simple, well-defined structures. Like tetracarbonyl nickel is tetrahedral, pentacarbonyl iron is trigonal bipyramidal, while hexacarbonyl chromium is octahedral. Decacarbonyl dimanganese is made up of two square pyramidal MnCO5 units joined by Mn-Mn bond. Octacarbonyl dicobalt has cobalt-cobalt bond bridged by two carbonyl groups. So let's understand these different carbonyl compounds and their structures as we have seen. And that's why in complex or coordination chemistry, these are of a special interest. The metal carbon bond in metal carbonyls possess both S and P characters. These are not simply just the S bonds or pi bonds. The metal carbon sigma bond is formed by donation of lone pair of electrons on the carbonyl carbon into the vacant orbitals of the metal. The metal carbon pi bond is formed by donation of pair of electrons from the filled d orbitals of metal into vacant antibonding pi star bond orbitals of carbon monoxide. The metal to ligand bonding creates a synergetic effect which strengthens the bond between carbon monoxide and the metal, or CO and the metal. So this is how it's give and take relationship between carbon monoxide and a metal. The sigma bond is typically formed between metal, the donation of lone pair from carbon of carbon monoxide to the metal d orbitals. And the filled d orbital pair of electrons from metal is returned back and form pi bond with the pi orbitals of a carbon monoxide, of a carbon. And that's how that give and take relationship happens, and happens with the synergetic effect to strengthen the metal carbonyl bonds. So this is why it's typically very interesting kind of a complex formation. Okay, then let's understand the stability of coordination compounds. The stability of complexes in solution refers to degree of dissociation between the two species involved in a state of equilibrium. So stability is nothing but dissociation reaction happening between a complex and then the free ion, so to say. The magnitude of stability or formation equilibrium constant for the association quantitative expression of the stability is given by a equation. First of all, let's understand the equilibrium equation between metal and ligand. This is the forward reaction is nothing but a formation reaction of a complex, and then the reverse reaction is dissociation reaction. The large stability constant, the higher the proportion of Ml4 that exists in the solution. Higher the stability constant, larger will be the stability. Free metal ions rarely exist in the solution, so that metal M will usually be surrounded by at least a solvent molecules, which will compete with the ligand molecules, and be successively replaced by the ligand molecules. So you are actually replacing water molecules in the complex, in a solvation, by the ligand molecules. For simplicity, we generally ignore these solvent molecules like water molecules, and that's why we write 4 different equilibriums like this, and that's why we have 4 different equilibrium constants as well. Where K1, K2, these are referred to be stepwise stability constant. Alternatively, we can write overall stability constant as well by showing an equation combining all ligands together. So this is typically an equilibrium constant or overall equilibrium constant between these reactions. Now, stepwise and overall stability constants are therefore related by a common formula where beta 4 is equal to K1 into K2 into K3 into K4 and furthermore. So the relationship between beta 4 and the stepwise constants can be given like beta 4 is nothing but a multiplication of K1, K2, K3 and K4. If we take an example, the steps involved in the formation of copper ammonium ion, we have following equation. So copper ammonium means copper ammonium complex. So the first ammonia molecule attaches to the copper to give first complex, which has a stability constant or equilibrium constant basically like this, K1, and then the second one with this. So beta 4 for this particular copper ammonium complex can be written as beta 4 and this expression. The addition of 4 amine groups to copper shows pattern found for most formation constants, in that the successive stability constant decreases. In this case, 4 constants particularly are this way: log K1, log K2, log K3 and log K4, whereas log beta 4 is 11.9. The instability constant or dissociation constant of coordination compound is defined as a reciprocal of formation constant. It goes unsaid. When you want to calculate instability constant or dissociation constant, you just take reciprocal of this K1, K2, K3, K4. or overall you can take a reciprocal of beta 4 as well when you want to calculate the instability constant. So let's calculate the overall complex dissociation equilibrium constant for tetraammonium copper ion given beta 4 as 2.1. so this is one example, a numerical. Let's try to solve this. Okay, here the overall complex dissociation equilibrium constant is the reciprocal of overall stability constant beta 4, and that's why we have been given beta 4 as equal to 2.1 into 10 raised to 13. So the overall complex dissociation means instability constant, basically they want to say instability constant. So that's why you can calculate it by taking reciprocal of this beta 4 to give you 1 upon this particular term, and so if you calculate that, it comes to 4.7 into 10 raised to minus 40. Remember, higher the dissociation or instability constant, lesser the stable that complex, and higher the stability constant or overall complex dissociation overall complex formation equilibrium constant, then more the stable that complex ion. So with this we are at the end of this chapter, and I'll share with you rest of the questions and answers from NCERT and then additional question and answer as well on the group chat. All right, thank you so much guys.